Thank you for the introduction and thank you so much for inviting me. I'll be talking about joint works with Ivan Losev, Lucas Mason-Brown, and Cyril, and ongoing work with the same people. So the goal is to understand basically better duality between nilpotent order slices on one side and some covers of nilpotent orbits on the other side, which I believe was expected to hold for a long time. We proposed a candidate for dual to nilpotent order slice in a work with Ivan and Lucas, and they'll start talking about that. So you can see the plan. First, I need to explain what actually I mean by symplectic duality. We do not provide any gauge theory that have Higgs Coulomb branch because of the things we want. We just look at the invariants and try to guess what things should be dual by just looking at them. And then to understand this invariance, I'll need to talk about geometry of nilpotent orbits, what's happening inside nilpotent core, and how we can actually compute this invariance. And then at the end of the talk, I will talk more about what we did with Lucas and Shelin, that we try to extend duality so we can have non-special orbits appear, because there is a parallel representation theoretic picture in which there is nothing special about special orbits. We care about all orbits in the same way. And finally, I will try to explain what geometry I can see here and what, in my opinion, is actually happening. Okay, so what invariant do I care about when I talk about symplectic duality? So if we have conical symplectic singularity, then we do have dynamic cover space that parameterizes Poisson deformations. Namely, we take a Q factorial generalization when we have a symplectic resolution. It's just symplectic resolution. In general, we might not have it, so we just resolve open dimension two singularities. And then we just look at the second cohomology of regular walls. Yeah, and an important theorem that Poisson deformations are parameterized by the quotient of the space by dynamic output, certain finite loop. That's one invariant I care about. The second is that, again, if I have this symplectic singularity X, I do have a group of graded Poisson automorphisms. I need it to be conical here. And then I just look at the maximum torus inside and take a Lie algebra. Now, both P of X in the previous slide and this T are just vector spaces, and the expectations that we use to guess what should be vector dual varieties are that on symplectic duality, these vector spaces should be interchanged. And there is a more complicated relation between the vowel groups that I first won't have time to get into. Okay, now, as I said, for me, the most interesting examples come inside nilpotent column when I have nilpotent order slices and I have some nilpotent orbits or other covers of them. So the general setup is that I work always over the field of complex numbers. I look at the simple Lie algebra and corresponding adjoint group, which you can take semi-simple, but everything will decompose into what happens on simple factors. And the objects I care about are nilpotent orbits and their finite J-equivalent covers. I need to understand this invariance for nilpotent orbits, I need to reduce them to some basic blocks. For nilpotent orbits, my basic blocks are distinguished orbits. So I do have a Bauer-Carter classification that first I can saturate orbits, meaning that I can take a Levy subgroup inside my group. I can take a nilpotent orbit inside this Levy. Now, of course, L accent, and now instead of acting by my Levy check, I act by all group G check. I'll get an nilpotent orbit inside G check this way. It's called saturated, and the orbit is distinguished if it cannot be saturated from any proper value. For example, In type A, the only distinguished orbit is just regular orbit, but in other classical types, there are many distinguished orbits. There are combinatorial conditions that can describe it. And the theorem due to Bauer culture is that up to G conjugation, there is a unique pair of a levy from which we can saturate, and a distinguished orbit inside this levy that saturates given one.
I'm sorry, if you go back to the
Yes. Sorry, I don't hear you. Where it's about basically you take a parabolic subgroup and you take the reductive part of it. Alternatively, you can look at it that you have your linking diagram, you take some subset of roots and generate the subalgebra by these roots. Okay, and now we can use this Bauer-Carter classification to describe our invariants for the nilpotent solid slice. So first, what is this object? That I take an element of my nilpotent orbit, I consider an SL2 triple attached to it. Then I look at the solid slice, which is just that I take a point to check my orbit, and I add an affine space which is cardinal of the adjoint action of F check. These are elements of the algebra, so I do have a joint action by commutator. And that's the full solid slice. What I want is nilpotent solid slice. It's just given by intersection with nilpotent code, union of all nilpotent orbits. And an important theorem by Mikhail and Sorger is that in most cases, when we look at the numerical space of X chair, we will just get dual Cartan to the linear algebra in which we work. And we can explicitly describe when this is not the case. And it happens when we have the same nilpotent solid visualized to our orbit O check in G check and to some other orbit in linear algebra of larger rank. And then the theorem just holds without this note for this bigger, higher rank linear algebra. So a typical example is if we look at the slice to subregular orbit in SL2n plus 1, so it's rank n linear algebra, we will get a Kleinian singularity of type A to n minus 1, just quotient of C2 by a cyclic group of order to n. But it's the same that slice to subregular orbit inside SL2n, which is rank 2n minus 1 linear algebra. And the numerical space will be dual to the Cartan of SL2n. And the second invariant we cared about is what was the maximal torus. Yes?
Well, that's a good question.
So, what was the maximal torus? And really, since it's a vector space, and we compare just vector spaces, we care about dimension. So the dimension is just the co-rank of this value. If we talk about linking diagram and we just picked some nodes and generated by everything, by simple roots outside of these nodes, then it's how many nodes would be. Okay, so that gives us an answer what are the invariants for nilpotent solid slices. Second, we want to understand invariants for orbit covers. For this, we also need to reduce everything to building blocks in a similar way. That here we reduce the distinguished orbits. And first, it's not quite there. We can talk about Lewis-Exponent-Stein induction. That again, we have a levy, we have an orbit inside the levy, and we want to produce an orbit inside G. G star. So we do it a different way here, that we look at the variety which is closure of L times orthogonal space to the parabolic. So we pick any parabolic, it doesn't depend on the choice, that has our value as a value factor. Then we do have an action of our parabolic P on this variety. So we can form a fiber bundle over G mod P with this given fiber. Now we do have Hamiltonian action of G here, and therefore we have a moment map to G star. And theorem due to the exponent time is that the image of this map contains a unique open dense nilpotent orbit O. So this map factors through the closure of O. This orbit is called induced, and again, if we cannot induce from any proper levy, we say that orbit is rigid. So issue with this construction is that we don't have an analogous statement to Balakartov theorem. For a given nilpotent orbit, there may be several pairs of a levy and a rigid nilpotent orbit that induce it. So we need to first of all be able to talk about covers and not orbits, and second fix this issue. So for this, we need the notion of birational induction. So we have the same setup, but now we also allow equivariant coverings of an orbiting levy. We need to take closure, but because it's not clear what closure of nilpotent cover is, so we take affinization of it. Take algebra functions and spare of it. If we just have an orbit itself, then if the closure is normal, we just get the closure. If the closure is not normal, we normalize it. So for the case of just nilpotent orbit, it's almost the same, and let's do it for generalization to covers. Again, we do have a moment map to G star, and the image will be the same, both of the same orbit O, the loose exponent sign induced orbit. But now we can talk about color, which is just the preimage of this orbit under the moment map. Let me also note that it's clear here because we started with a coloring, but even on the previous slide, this map rho is not in general birational. So even when we start with an orbit, this preimage rho inverse of O that I consider may be a color. Okay, but anyway, we do have some equivariant covering of O. We say that it's birationally induced from pair of levy and a nilpotent cover for this levy. Similarly, if we cannot birationally induce it from any proper levy, we say that it's birationally rigid. And these objects behave nicer with respect to Balakartov type of theorem, because we do have it. Up to a conjugation by G again, there is a unique pair of levy and a birationally rigid cover, from which we can birationally induce the given one. Now, using this, we can parameterize the invariant we care about, the Merkava space and the maximal torus, for nilpotent orbit covers as well. So, of course, we want a fine conical singularity, we need something affine. So again, we take the affinization of our nilpotent orbit covers. And as we discussed before, there is a unique optoconjugation pair of levy and birationally rigid cover attached to it. I'll call it for birational induction datum. And the theorem basically due to Ivan he proved it for nilpotent orbits, but the proof basically carries on for covers. that the Namikawa space is isomorphic to, basically it's dual to the center of this valley. So we take quotient by the semi-simple part, take dual. Now, that is always true. We need to also understand what is the maximal torus. And what, therefore, is the maximal, is this group of graded Poisson automorphisms. And in almost all cases, this group of graded Poisson automorphisms is just the group G itself. It acts on our nilpotent cover, respecting symplectic form. Therefore, it acts on affinization by graded Poisson automorphisms. And then the torus is just the Cartan space. There are exceptions, similar to how there were exceptions when we computed the Namikawa space for Sodry slices. This is what's called shared orbits. They were studied by Kostent and Brzezinski, when, again, we have our cover of orbiting G, and we have a cover of some nilpotent orbit in a group of higher n. And the algebra functions are isomorphic. Therefore, in these cases, we do have a larger group of graded Poisson automorphisms. It's just this G prime. And Kostent and Brzezinski provided for which the algebras it can happen and some examples of shared orbits. But now these shared orbits are completely classified by a recent work of Fulvito, Levy, and Soros. So we know all cases when it actually happens. And again, in this case, the group of graded Poisson automorphisms is just G prime, so the maximal torus is H prime. So again, we can understand these two things. Now, using this knowledge, what we did with Lucas and Ivan is try to construct a map where we take nilpotent Sodry slice to an orbit or check what should be the dual cover so that these invariants are interchanged. First, to have some kind of a guess, I think it was known well before us that they should be connected. There is a notion of Barbour-Borg and Lucis-Wolkenstein duality. How we just go in general between nilpotent orbits on both sides. And the construction is as follows, that we have our nilpotent orbit in O check. We can take an SR2 triple. We can always assume that the semi-simple part lives in Cartan. Then we do have an element of Cartan, which is 1/2 H check. In fact, it is only defined up to the action of the while group. Then we do have a center character. And we know that center characters are in bijection with maximal ideals in the personal open algebra. So when we start with a nilpotent orbit or check, we can construct a maximal ideal coming from it just using the center character 1/2 H check. Now, for an ideal inside universal enveloping algebra, we can consider its associated variety just because we do have the Poincare-Birkhoff-Witt filtration on universal enveloping algebra such that associated graded is symmetric algebra of G. Then if we do have an ideal inside the universal enveloping algebra, we can obtain this way an ideal inside symmetric algebra of G, which is the algebra functions on G star. So we define some closed variety inside G star. And if we start with maximum, in fact, any primitive ideal, this associated variety is always a closure of a single nilpotent orbit. That's in fact due to Joseph. And Then we can go from orbit on one side to orbit on another side. It follows. Start with a nilpotent orbit or check, construct the ideal, look at the associated variety, with the closure of a single nilpotent orbit. That's the nilpotent orbit we're looking for. We will not get all orbits this way. So the orbits that are in the image of this map are special orbits. They are originally defined in a completely different way by Lustig, but an equivalence of a definition. In type A, again, every orbit is special, but in other types, this is not true. Okay, that gives us a map, and I think it was known for a long time that Swordless slices to or check should be related with O somehow. Now, since we do have this classification of invariants on both sides, for nilpotent Swordless slices and for orbit colors, we know that the maximal torus for Swordless slice comes from the Lorcato classification. And the Lemaitre space on the dual side comes from the bidirectional induction data. Then what it tells us is that if we have a distinguished orbit, so the maximal torus is trivial, then the dual thing should be bidirectionally rigid. So the Lemaitre space is trivial. There are no deformation. And then the first, and we already have somewhat of a guess what it should be, just because we have this Barbara-Fogg and Lustig-Spollenstein duality map. But we need to modify it a little bit. Namely, that if we start with a distinguished orbit, and we just look at the Barbara-Fogg and Lustig-Spollenstein dual, it doesn't have to be bidirectionally rigid. But if you look at the universal cover, it is. And so, our proposal is that when we want to compute slice dual to nilpotent Swordless slice to distinguished orbit or check, we take the universal cover of the dual orbit. Now, for the general case, we know that when we saturate on one side, so we every time increase the dimension of the maximal torus, on the dual side, to increase the dimension of the Lemaitre space, we have to bidirectionally induce. So in general, we define this map that for O check, general nilpotent orbit, take the corresponding Bellacauter pair, take dual to the orbit inside Levy, take universal cover of it, and bidirectionally induce to a cover engine. And so what are good properties of this map? That first, we always get the equivalent cover of just Barbara-Fogg and Lustig-Spollenstein dual, so in particular we always get special orbits. Second, that this map is injective, which was not true for just the usual map. And the third fact that will be important later, that if I have some cover, so I can look at the Goa group of this cover. The Goa group of this cover is isomorphic to Lustig quotient of object. Definition of Lustig quotient is somewhat technical, I won't give it, but kind of it's a really important group that appears somehow everywhere. And yeah, basically summarizing the discussion before is that the invariant Lemaitre space and maximal torus are indeed swapped, and the relation about Weyl groups that I haven't stated also holds in this case. Okay, but now when we have this, there is a nature question: what should be the symplectic dual to a cover of non-special orbit? Because there's parallel presentation theoretic part about nilpotent ideals, And for each, there is no difference between special and non-special orbits. And some questions that just more indicate which approach about I want to take is we expect that still the answer is related with nilpotent orderly slices. And for nilpotent orderly slice, we do have the corresponding to special orbit and color we just constructed. So there should be some relation, and we should be able to say something about non-special orbits just from knowing all the information about special. And now, the way of rephrasing it is, if we just look at the special piece, I will define with this later. What can we say about geometry? So the last two topics I will touch at the very end. Let me just explain what we do with Lucas, Mason Brown, and Sherin. So we want now to have a map, duality map, again, to colors such that in the image we also have non-special orbits. That means that we cannot start just from an important orbit on the dual side. We need to enlarge the set we're working with. And basically we use ideas of Alex Thomas and Clement Chow that basically suggested in work of Seong that the correct object is now a pair of an important orbit, as before, and a conjugacy class of Lustig quotient of this orbit. Here I should make a comment that Lustig defined canonical quotient only for special important orbits, but the definition can work and done by Somers for any important orbit. So here, when I talk about Lustig quotient, I do not assume that orbit is special. It can be any important orbit. So now we do have these pairs of an important orbit and a conjugacy class. We do have a very similar statement to the standard Bell-Coulter theorem for these pairs. Namely, we want to be able to saturate. We know what it means on the level of orbits. We just need to understand what it means on the level of conjugacy classes. And now, what are my Lustig quotients? They are just some quotients of the usual fundamental group of orbit. And this thing is a quotient of the centralizer of an element here. Now, it is the same element, because the way our saturation map works is that we take one important orbit, and first we act by L check, and now we act by G check. So we can pick the same important element, and now one stabilizer is just a stabilizer inside L check, another one is inside G check. So of course we do have an embedding. And it is some check that we did that when we go to the quotients, we still have a well-defined injective map. Then we can saturate Lustig-Achar data. And just we saturate the orbit and apply this map to conjugacy class. Or take the representative and apply the map. And we do have again a Bell-Coulter style result that there is a unique up to conjugation triple of a Levy and important orbit and conjugacy class. Basically, the reason why we do it is because we expect that the dual is some modification of important orderly slice. So again, we want the maximal torus, or whatever we consider, to be of dimension of co-rank of this Levy. Now, what should be on the dual side? Again, if we already had an idea of what should be dual in the classical case by Balbo's program map, here we do have an idea coming from the work of Somers. That he constructed a map from this set to nilpotent orbits such that if we take trivial conjugacy class, we just recover the usual duality map we were talking before, particularly we get special orbit. But if we look at the all conjugacy classes, we get now a surjective map, but not injective, I should say. And again, our idea is that if we have, I need to restrict now to a smaller subset of spatial Lustig-Achar data. I probably won't have much time to talk about it. It's another technical condition that we know how to check it in classical types combinatorially. Achar has in tables listed all of the special and non-special pairs for exceptional types. Basically, it's a small, it's a bit smaller subset, but containing most of the pairs. So if you restrict to it, then again, the idea is that if we start with something distinguished, we should get on the dual side something bilaterally rigid. In the original case, we had basically two cases. One was not correct, that it's just an orbit, another that it's universal cover, which was correct guess. If it's exceptional types, it's still correct guess, but in general, we need to take something in between. We can produce an exact cover and describe it, so there is a natural relationally rigid cover of our orbit that we will take as dual. And let me also note that the notion of special that I kind of omitted is really important here, that things just do not work actually for any results that one can expect for non-special pairs. Now, when we do have this, we want to get the duality map for general Lustig-Achar pairs. We do it in a very similar way, that we do have Power-Culture's theorem for them. So again, we just look at the pair of a Levy and a distinguished Lustig-Achar datum. We take the bilaterally cover we just constructed for the distinguished one, and we bilaterally induce it.
Can you show the previous example?
Sorry?
Could you explain to what was the example?
That example was when things don't work. So yeah, if we take in E7 orbit A4 plus A1, then I believe in this case A bar is isomorphic to S2. And if you take non-trivial conjugacy class, then the dual orbit does not admit an adjoint equivalent cover. Like an interesting fact is that if we allow G to be simply connected, the universal cover is bilaterally rigid. And it often happens, but we don't have a distinct pattern to really explain it.
How high is this?
The dual orbit, I don't remember right now. I should look at the tables in a chart. Okay, so, and again, let me list some properties of this map D. Is that first, it refines Sommer's map in the same way that the earlier map to covers refined Barber-Fogan map. That we always have a J-equivalent cover of Sommer's dual. Second, when we have trivial conjugacy class, we just recover the earlier map. And third, that, yeah, this map is injective now. Okay, now, how do I think about this nowadays? Is that I really want to understand this map and this non-special orbits by just looking at the special ones. So first, some geometry of nilpotent goal is that we do have a special decomposition of nilpotent goal. I believe it's due to starting sign. That take arbitrary nilpotent orbit, then we do have a partial order of nilpotent orbit just given by the relation that one orbit is smaller than another if lives inside the curve. So the condition that I have here on O and OSP is just defines me partial order. Then I can look at all special nilpotent orbits that are bigger than my orbital. And there is always a unique minimal. So therefore, I can decompose I can just first for every special orbit look at all nilpotent orbits such that for them this unique minimal special is exactly my OSP, and I call it the special piece of OSP. And since I have a unique statement, it tells me that the nilpotent goal is just decomposed into disjoint union of special. And another fact that it's clear now from the construction that each special piece has a unique maximal orbit is exactly the special one. But it also always has a unique minimal orbit. Okay, now why does it matter? It's because I want to be able to look at the special piece and say something about it and all orbits inside, just slow looking at the biggest orbit. How do I do that? I want to look at the slice to the minimum orbit in the special piece in the closure of the special one. And it is surprisingly nice. So again, the setup is that I take basically the intersection of nilpotent Swordley slice to my minimal orbit in the special piece, and intersect it with the closure of the special orbit, the biggest in this special piece. And it is always a quotient singularity. So basically, it's a disjoint union just because I want to write it as a quotient of by a bar, the Listy quotient. So the way I look at it is this way. I look at the cover of my special orbit corresponding to the kernel of the map from pi1 to the Listy quotient. I take affinization. Then I want to look at the preimage of the special piece inside this affinization. And the claim is that it is smooth. So, and then, well, it looks just as a symplectic vector space, but we don't know that it's connected. And in general, it is not. So it lives as some disjoint union of symplectic vector spaces. And now I have a Galois group, a bar, acting on this cover. And first, it permutes all connected components. So despite this simply being disjoint union, when we take the quotient, we will get something connected. And when we look at so we have a map, say, to SK, semantic group on K element. And if you look at the kernel, this is a subgroup that was predicted by Lustig. And locally, this slice looks the quotient of a symplectic vector space by this subgroup. For me, it's easier to think about it as just we take quotient by the Listy quotient, mostly because I don't really understand the Listy subgroup yet. Probably it's a better language, but I am. Yes, so in classical types, a bar is always a product of several residues. And in this case, we can describe it that basically we have two types of object. We have one-dimensional representation of Z2, so we just have a quinine singularity. And we have a minimal singularity of type C. When we take n-dimensional vector space, take a tangent bundle to it, and take quotient by Z2. Yes, this is above special orbit.
Special, it's possible that special orbit.
In classical types, it is always true for any orbit. In exceptional types, it is generally not true. Well, it's always symmetric group.
Yes, but I'm asking if it's possible that the special piece will be made out of four, let's say, C equals to
Yes. Yes, it is. For example, if we take orbit 53311 in SOCT, so type B6, it will be the case. It is a special orbit and it has four orbits in the special case.
Then you're saying it's a C some.
Yes, yes. But basically, locally, we always can write it as sum of just quotient by Z2 of some vector space. That's really what happens. So yeah, like an example is that we can have C2 quotient by Z2 twice here. And yeah, so my next point is that to understand orbit in the special piece, we just need to understand geometry quotient singularities. And therefore, we need to understand parabolic subgroups of A bar, or rather of this Lustig subgroup. And in this example of C2 quotient by A1 plus C2 quotient by A1, we do have parabolic subgroups. So the group is Z2 times Z2. We have a parabolic subgroup corresponding to one copy of Z2. It gives me one quinine singularity of type A1. I have another generated by another copy of Z2. It gives me another copy of quinine singularity. And I have sync, which is just generated by everything, and it gives me a single point, 0. And of course, I have trivial that gives me everything. Okay, but now, how is it related to what I discussed before? So let me go back to my pair O check C. We, in all cases, of course, C is just an element of A bar, even in conjugacy class. So it doesn't really act on my nilpotent solid slice. What does act on nilpotent solid slice is the centralizer of SL2 triple. And this is some quotient, it lives in some quotient of it. But we construct a natural, in our sense, lift of this element C to a semi-simple element inside this group of finite order. Now, what it gives us is that we have a finite group, just cyclic generated by S, that acts on the nilpotent solid slice. And basically, the proposal is that dual to our orbit cover should be the nilpotent solid slice remembering this finite group. What exactly it is not quite clear at the moment. So yeah, the thing that I mentioned before in the properties of our map with Lucas and Ivan is that the Galois group is isomorphic to the Lustig quotient of O check. What it means now is that we have this group gamma acting on both sides. On one side, it acts because, I just constructed it to live inside the subgroup that acts. On the other side, it acts because it lives inside a bar, which is the Galois group. And what we expect, well, there is no written proof. I think I understand that in classical types, we haven't really worked much on exceptional yet, that the color that we get is just obtained from the color for the trivial conjugacy class, and then we take fixed points with respect to this finite group. So like an example when the slice, again, everything can be reduced to the slice to the minimal orbit when we want to look locally. And here an example before when we have A1 plus A1, if we take a look at the fixed points with respect to Z2 that acts on the first part of C2 plus C2, then we exactly get our C2, our A1 singularity that lives on the second part. So that's basically the idea of what's happening. And that's the result we expect. And now let me end with the last slide. What would it mean? Is that now if we know that our variety is just a set of fixed points, if we assume that this statement that we propose is true, then we can directly compute the Nemikawa space and the maximal torus for it. But again, here I don't really use that it's fixed points. I really use that I know what orbit it is and how to compute it for nilpotent orbit colors. And then the Nemikawa space and the torus are just fixed points of the respective Nemikawa space and maximal torus. And an interesting observation is that if we take fixed points on the dual side, so fixed points of the Swodevy slice, in most cases we get the same invariance we need, but we won't get the same Weil groups. So like this guess basically was inspired by a discussion with Rak-Kyeong, and it seems almost right, but not quite right. So that is kind of the idea that I'm working with. Maybe I can something work with it. But what I am confident is that it should be some modification of nilpotent Swodevy slice that counts in the estimate term. Okay, that I think I'm definitely out of time. So thank you.